Hello, my name is Richard Perez from the University at Albany, State of New York, USA, and I would like to talk about implicit storage-enabled firm PV power forecasts as a step 1 to optimum ultra-high PV penetration. I would like to acknowledge my co-authors from Clean Power Research and the University of Rome, and I'm introducing some concepts that may be new to you, like implicit storage, firm PV power forecasts, and how they relate to ultra-high PV penetration. So firm PV power forecast first. This is my forecast for tomorrow, say, and even the best forecasts are not perfect. In that case, I overestimate in the morning and underestimate in the afternoon. However, the predicted output, my forecast, could be guaranteed using hardware, storage to make up for over forecasts and oversupply and curtailment to make up for under forecasts, thus delivering firm forecasts to the grid operators. And that oversupply and curtailment of PV is what we term implicit storage. And I will show first that it's an effective strategy to deliver zero uncertainty information for PV fleets vis-à-vis the grid. But most importantly, that it constitutes a very effective strategy to deliver, at the end of the day, firm dispatchable PV available 24 hours a day, 7 days a week, 365 days a year, a necessary requirement for ultra-high PV penetration, firm power generation. So let's have a look at firm PV power. This is a scale of LCOE. And the intermittent PV, the unconstrained PV, is very cheap. We know that. It's probably the cheapest way to make a kilowatt hour of electricity today in many parts of the world. However, delivering a firm PV kilowatt hour available all the time costs a little fortune because of the amount of storage, of seasonal storage needed to accomplish that. And this is even when using the lowest cost future projection of storage. Unless you oversupply the PV and curtail it by design, spill some of the output by design, and when you do that, something quite interesting happens. So the white line represents the LCOE of the firm power, the blue line is the contribution of storage, and the red line is the contribution of PV. So PV goes up because you overbuild, but storage goes way, way down, and firm power gets to a point where it can be nearly affordable. And we've shown that in a series of high visibility studies throughout the world. The latest one is the one we did for the mid-continent system operators in the US, a large interconnected region ranging from the Gulf of Mexico to Canada. And in that case, we showed that by 2040, we could have firm power dominated by PV, 55% PV optimized, 40% wind and 5% natural gas, at less than 5 cents per kilowatt hour. And this is why you see that we started calling oversupply and curtailment implicit storage, because it acts as a catalyst to storage, enabling the storage to do what storage does, meaning supplying power when there is no output, but doing it at much, much lower costs. You can see more of that study at that website right here. So this is the logistics of firm forecast. The job is to transform the actual PV production to the one I predicted, say 24 hours ahead. And it's no different from the logistics of firm power generation, transforming actual PV production into load shape. The job is just much harder. So let's look at the numbers in a case study we just completed for the New York ISO, a grid operator that covers the state of New York. Peaks at 32 gigawatts. It has 11 electrical regions, and for each regions we looked at single plants, and we looked at homogeneously dispersed fleets, and we also looked at the entire NISO interconnected with PV. We looked at different levels of flexibility from 0% to 5%. And in terms of grid penetration, we start near zero, where the order of the day, the necessary duty cycle is to deliver firm forecasts. And for forecast, we applied the Solar Anywhere forecast, which is an optimized blend of NWPs and satellite-derived forecast, which is operational throughout North America. And then we evolve penetration all the way to 100%, where the job to be done is to deliver power around the clock without fail. This is the load shape that must be met. So starting at low penetration, the load shape consists of the forecast. So it's not much different from PV output. And as I increase penetration, that load shape evolves and morphs into the actual grid load shape, which is quite a different from solar. You need power at night, and you need quite a big difference in the winter season. So you can see the job getting much harder as penetration increases. And that's what it takes to do the job in terms of storage and in terms of implicit storage. So on the left, the x-axis is grid penetration, and the y-axis is storage in number of PV hours. And on the right, the y-axis represents the overbuild, the optimum overbuild. And I see that when I add flexibility to the system, the job is getting noticeably easier to accomplish. But the real question is, how much does it cost to do that compared to unconstrained PV? So there is a small premium to pay at the forecast level on the left, and that increases steadily all the way to firm power generation. This is for current technology costs. If I look at future costs by 2040 for PV and storage, this will be, I will start from a very small premium to pay to go from unconstrained PV to forecast guarantees 24 hours ahead, all the way to 4.5 cents per kilowatt hour at firm power generation in New York, which is not bad. But the real value is when you compare to what if you don't do implicit storage. This is how much you would pay, close to 10 times more for that firm power. Here on the same scale is what you accomplish using implicit storage. So that's where you see that the strategy is very, very effective. And there is not much of a difference on the left side when you start from current condition and low penetration, but it really accumulates when you move towards high penetration. So the sooner we start, the better it is. It's interesting to look at the impact of regional interconnection, especially with respect to transmission. So this is for 1 hour forecast, comparing the premium to pay over unconstrained as a function of the regional area. So it's cheaper to do the job for larger area. Understandable, you average the weather, it's either to remove that uncertainty, but that tends to disappear for longer time horizons and totally disappears, in fact, when you talk about firm power generation. In fact, what drives the firm power generation premium is the actual resource that you see for New York here. Very interestingly, another way to put it is to look at how much more would I pay if I deal with regions one by one as opposed to interconnecting the whole NISO. So for 24 hours forecast on the left, it makes quite a difference. You want to interconnect to average the weather, but when you reach high penetration, the difference is quite small. And this is a very, very fundamentally important result, because it tells you that inter-regional transmission is not critical for ultra-high penetration. You can almost do the job regionally. So that brings in a lot of localized resilience possibilities. So in conclusions, we've shown that a firm forecast strategy can be economically justifiable today, that applying storage, both real and implicit, constitute a very effective entry step to achieve least cost ultra-high PV penetration when firm power generation will be a prerequisite. The NISO case study points that a 2040 target ultra-high penetration straight business LCOE of 4 to 5 cents per kilowatt hour could be achieved with implicit storage. It would be about 10 times that without, and straight business cost is without incentives. And finally, firm power generation could be contained within electrical regions at a modest cost premium that decreases with penetration. thus alleviating the need for major trans-regional grid buildup and promoting localized resiliency. So this last result is fundamentally important. And on this, I will thank you for your attention and take questions.